I think I'm live. Hi everyone, and welcome to another day for this 29-day challenge. Uh, so what we are doing essentially here is that every day we'll be solving around two problems from different topics, and it can be anything, right? And the idea being that I'll be also giving you a few problems for your homework. The idea being that by the end of 29 days, you should have a significant of problems already solved. And not only that, when you actually you develop that habit as well, so that you can easily complete the entire list set of problems that are generally asked in interviews. So here we have targeted Amazon, uh, right? And yeah, like that's most of the agenda. So today we'll be discussing about two more problems. The first problem that we'll discuss today is parenthesis checker. It's a very easy problem. And after that we'll be discussing about the get minimum element from a stack. This is also not very difficult question. It's also easy, but again, like there's a trick involved here. So we'll look into that trick as well, right? And after that, I have three problems for your homework as well. Out of them, it's stack using two queues, which is a easy problem. Next, creator element. Now this is a very important problem when it comes to interview point of view, but again, I have already discussed this problem in another video in the same channel. So if you want to look into the explanation about how to solve the next creator element or the variance of next creator element, you can definitely check that video out. Other than that, the last problem will be queue using two stacks. It's also a easy problem, right? So just solve these problems for your homework. But let's start today with the problems that we will solve today, that are parenthesis checker and the get minimum element from stack. So the parenthesis checker is pretty simple question, and it's a very popular one as well. I believe like most of you already have solved it or you have heard it definitely. So given an expression string x, examine whether the pairs are of ordered braces, brackets or square brackets are correct in expression. For example, the function should return true for the expression. If you see that this is a valid parenthesis sequence, like here we have a opening one, then we have a opening bracket, closing bracket, so these forms a pair. Then we have a closing square bracket, so this forms a set. After that, we have a opening brace and a closing brace. Then we have a opening brace. Then we have a opening square bracket. Inside that, opening bracket and closing bracket paired, opening closing. Then the closing square bracket. So this forms a perfect match. And after that, we have another bracket. After that, we have closing brace, which basically forms this, right? So we have to tell whether it is a valid parenthesis string or not. That is valid parenthesis string or not, right? So and this will be false, right? In this case, if you see, we have a square bracket. After that, we have a bracket. Then we have a square bracket closing, right? But this square bracket closing, how will this is not closed yet, right? This is not closed yet when the outer one is getting closed. So this is not a valid one. This is not a valid sequence, so it should return false. Now it's pretty simple. It's very simple, right? So for this example, we have to return true, because if you see, it is a matching, it's a valid parenthesis sequence. Here is the opening closing, opening closing, opening, right? uh, so this is false because it does not have a closing. So this is the question. How can we solve this? I'll just discuss quickly. Like, I'm pretty sure that you already know about this, but again, like, let's just discuss a bit quickly if you don't know about it already. What we'll generally do here is we'll take a stack, right? We'll take a stack, and here, if we see a opening bracket, right? Opening bracket, be it this one, be it this one, be it this one, we will push it into the stack. So let's take a expression. Let's take a expression that is a square bracket followed by a brace, then this one, then this, then this, then this, right? This is the valid one. So what we'll do is, when first we'll start from the first character, it is a square bracket opening, right? So we will push it into the stack. It's a square bracket opening. After that, we will have a brace, so we'll push it into the stack, telling that it's a brace opening. After that, we have, whenever we see a closing bracket, we will check on the top of the stack. If on the top of the stack we have the opening bracket of the same type, only then it is valid, right? We can remove it. So we see that on the top of the stack we have a opening brace and it is a closing brace, right? So these are of the same type, so we can remove this safely and we can proceed. Then we see a bracket is coming here, so we'll insert it into the this. Then we see a closing bracket, right? Now we'll see in the top of the stack, if the top of the stack has an opening bracket of the same type, then we will remove it safely, right? So it has, so we'll remove it safely. Then we'll go to the next one. Okay, here we have a closing square bracket. What is at the top of the stack? At the top of the stack we have a opening square bracket, so we can remove it safely. And then we proceed forward. We'll insert this. Why are the recordings of the session not posted? Which recordings? Which recordings are not posted? Sorry. Okay, after that we have a closing, and we'll see what is at the top of the stack. It is opening bracket of the same type, so we'll remove it, and thus we reach the end. So this means that this entire string is valid. Let's take an example of invalid and see if that works, right? If the same logic works. So we'll take a small example. Let's say we'll take an example like this. This one. Can you tell which one? Akash, can you tell which one? Which is not? So this is invalid, right? So let's see how do we prove invalid. We'll start from this one. We'll push it into the stack. After that, we'll go to the next one. We will push this into the stack. After that, we'll go to the next one. This is a closing bracket, right? It is a closing bracket. What is at the top of the stack? At the top of the stack, we have a opening brace, and this is a closing square bracket. So it's not of the same type. So here we will cancel and will return false, that it is not a valid one, which is true, right? So let's take another example quickly and see if this is working further for different examples. So let's say we take an example like this, that and something like this. Let's say we don't close only, right? We don't close. So let's see what will be. So first of all, we'll start from this one. So this will be pushed into the stack. Next we'll go to the next type. It is opening, so it will be pushed into the stack. Next we'll go to this one, so it is opening as well, so it will be pushed into the stack. Next we'll go to the next one. It is closing, so we'll see on the top of the stack what is there. It is opening bracket, right? So it is of the same type, so we'll remove this and we'll go to the next character. It is a closing brace. What is on the top of the stack? A opening brace, so it is of the same type, so we can remove this from the. Finally we are done with the string, but see, the stack is not empty, so there is no closing bracket for this one, right? So that's why this is not a valid one. Will return false for this. So this is how I can solve this. The code should be like, I think the explanation, the solution should be pretty simple. But again, like, if you have any doubts, feel free to ask me. Let's quickly write down the code for this. So stack char s. So for int I equals to 0, I less than x dot size. We'll go through all the characters one by one. I plus plus. If x of I is equals to this one, or x of I. Okay, one more thing that I haven't discussed with you. Let's actually discuss that case as well. Just one more case that I had forgotten to. Let's say we have something like this, that we have a opening bracket coming before, right? Or we have an extra opening bracket, closing bracket, sorry. So let's say we have this, and this, something like this and this. So here first we will push it into the stack, right? Or let's say we just have something like that, something like this. So we'll push it into the stack. Next element will push this into the stack as it is opening. Next element, it is closing. On the top of the stack we have same opening type, so we'll remove it from the stack. Next element, on the top of the stack we have opening square bracket, so it is of the same type, so we can remove it. Finally, we are trying to close something, but the stack is empty, right? The stack is empty and we are trying to close something, so this is not a valid sequence, so we should return false. So that was the case that I didn't talk about, but we have to be careful about that as well. So for int x I equals to this, or x of I equals to this, or x of I is equals to this. right? All the opening cases. In that case, we'll just push into the stack. So s dot push x of I. Else we are going to the closing cases. So else, right? Else, we have to handle all the cases separately. So if x of I equals to this, and x dot s dot top. Okay, first is if s dot size is equals to 0, that means we have a closing bracket but not an opening bracket, return false immediately, right? So if x of I equals to this, sorry, closing bracket, and s dot top is not equals to this, then we'll return false. If x of I, similarly for the other two cases, is equals to this, and s dot top is not equals to this, return false. If x of I is equals to this, and s dot top not equals to this, then we will return false. And otherwise we should continue, all at like it's a proper, or otherwise we should pop, right? So s dot pop, otherwise s dot pop, right? We'll pop and we'll continue. Okay, finally we'll see if s dot size is greater than 0. In that case we'll return false. Now we have taken out all the conditions when it can be false, so we'll just return true. So when is this condition possible? This condition is possible only when the size of the stack is greater than 0 after this operation has been done. But this should have removed all the elements from the stack. So this means there has been some opening bracket for which we haven't, we don't have a closing bracket, right? So that's why the size is greater than 0. So let's compile and run. It's giving balanced. Fine. Let's try to submit. Okay, so this is working, right? Anyone has any doubts on this? Pretty simple question. Any doubts on this? Anyone? Let me know if you have any doubts on this. I'll revisit this if you have any doubts, but let's move to the next problem, because that's a pretty simple problem and pretty sure that most of you had already done that, right? So but again, like, it's important from interview point of view, so I felt I had to discuss that. But again, like, it's simple. Okay, let's solve this problem. This is a good problem. So you are given n elements, right? You are given n elements, and your task is to implement a stack which can get you the minimum in order of one time. So you will have three operations: push into the stack, pop from the stack, and get min. That will give you the minimum element from the stack, right? It will give you the minimum element from the stack, but the constraint is that all the operations should be able to be, you should be able to do all the operations in order of one time, and space is also order of one, right? So you can definitely think about, initially you can think about order of n space, but eventually you have to solve it for order of one space and order of one time, right? So that is the question. So you are given a stack, pretty simple question. You are given a stack and you are given three methods: get minimum, push into the stack, pop from the stack, push into the stack. For each of these you have to implement each of these in order of one time complexity, and bonus is order of one space complexity as well for each of them, right? So we have to do like this. Okay, let's understand first how do we maintain the minimum. Let's say order of one space complexity is not there, we are free to choose any amount of space we want. When do we want to allocate some space, or what is the problem with having the minimum, right? So what can happen is, let's have a stack here. Let's have a set of numbers, right? Let's have a set of numbers. Let's say 2 3 1 4 5 2 5, let's say 2 3 3 2, 4, 5, 1, something like this, right? So first 2 is inserted, then 3 is inserted. That's all. First everything is push. After that we have pop and get minimum operation. 2, 3, 2, 4, 5, 1. Let's say when you are inserting an element, you are also maintaining the minimum element in a variable, right? So you are maintaining the minimum element in a variable, like you are updating it whenever you are inserting an element. So when 1 comes in, you have the minimum element to be 1. Now when you are popping 1 out, how would you know what was the previous minimum element? You have lost that information, right? You have lost the information that 2 was the previous minimum element when you inserted 1, right? So you have lost that information. So to get that information, what can we do? We can, instead of storing in a minimum element, we can store in form of an array, right? We can store in form of an array. Rather, what we can do is we can store in form of a dq, that, or a q or something like that, 1 is the minimum, right? So we will insert 1 into this, or we can have a minimum stack as well. That will be storing the minimum elements. So when you have 2, so it is a minimum element, so 2 is inserted into the stack, and also here. After that you have 3, so 3 is not a minimum element. 3 will not be updated because 2 is already there, so 3 is pushed into this stack only. Then you have 2 again, so 2 is already a minimum element, so you can decide to push or you cannot push. Let's not push 2, right, because 2 is already there. Then we have 4. 4 is not a minimum, so it is pushed into the second stack. 5, it is pushed into the second stack. Then we have 1, so 1 is a minimum element, so 1 is pushed into the stack. So when you are removing 1, you can remove it from the top of the stack like this, that 1 is removed, right? Also, I think it's better to push 2 as well, because when you are removing this 2, you would actually have removed this 2 from here as well. So it's better to push 2 2s here, right? 2 2 1. And then when you remove 1, you just remove it from the top of the stack. It is gone, right? After that you have 2. So 2 is the next minimum, right? So this is a order of n space complexity solution. So you are basically storing the candidate minimums that were there, right? The minimums that you was there at some point of time, you are storing those values. And this will be order of n space complexity, order of 1 time complexity solution. Okay, I hope this makes sense. Let's take another example. Is there a better example here? It's only 3 to 1. Okay, let's store, like, let's say we are storing, let's have some other thing, like let's say 2 3 2 2 1 5 1, right? So we will maintain this stack, minimum stack. Now first we'll start from this element, push. 2 is pushed into the stack. Now minimum element will become 2, so the 2 will also be pushed into this stack, right? After that we'll come to 3. Can 3 be the minimum? 3 cannot be the minimum because 2 is already there, so we'll move ahead. 2, so 2 is the minimum, and this is also equals to 2, so we'll push 2 into this, both the stacks. Again we have 2, so we'll push 2 into both the stacks. Why are we pushing into both the stacks? We'll look into that. After that we have 1, so 1, again 1 becomes the minimum, so we'll push 1 into the stack. Okay, here let's say we have a 2 instead of a 1, we have a 2, let's say. So here this is 1, by the way, write it properly. 1. After that we have a 5, so 5 is pushed only in this stack, right? After that we have a 2, so 2 is not pushed into this stack again, because 1 is the minimum, 1 is the current minimum, right? Now when you are popping from the stack, let's say you are popping from the stack, let's see how that affects. So 2 is popped, so it is only popped from this stack, so it is removed from this stack, right? After that 5 is popped, so 5 is removed from this stack because this stack does not contain 5 on the top. After that you are removing 1. When we are removing 1, we see that 1 is present in both the stacks on the top, so we will remove 1 from here. We'll also remove 1 from here, right? After that 2 becomes the current minimum, and indeed 2 is the minimum, right? After that we see a 2, so we'll remove 2 from both the stacks. We see a 2 and 2 is present on the top of both the stacks, so we'll remove. After that we see a 3. I think there was a 3 as well here. So we'll remove the 3 now from this stack only, and then we see a 2, so we'll remove 2 from both the stacks, right? So that will be a order of n space complexity solution to get the minimum element. I hope that's clear. Now we will discuss about how can we do it in order of 1 space complexity, right? So whenever we are reducing from order of n space complexity to order of 1 space complexity, we will be undergoing some form of hashing, right? Hashing means we will be storing the value within the same stack itself. Like for example, when you look into problems where you have to find something from the array, right? You have to find something from the array. What do you generally do for order of 1 space complexity? You encode the same value within the same array somehow, right? So we will use a very similar technique here as well. What we will do is, the idea is that, let's say we are maintaining a minimum element variable, right? We are maintaining a minimum element variable that will store the current minimum element. Now when you are pushing into the stack, let's say current minimum element is given by min, and the current value that you are pushing into the stack is x. Let's say x is less than minimum element. So you will not exactly push x into the stack. Instead, what you will push here is that you will push some encoded form so that you can get the previous minimum element, because once you push into the stack, the current minimum element will be replaced to x, right? Because x is smaller than the minimum element. So you should somehow encode the previous minimum element when you push the element x into the stack. How do you maintain that? So what you can do is, we can store 2x minus minimum element into the stack. Now 2x minus minimum element will be less than minimum element, will be less than x, sorry. 2x minus minimum element will be less than x. Why is that? Because just think about it. 2x minus minimum element, right? So 2x means x plus x minus minimum element. So minimum element x is less than minimum element. So x minus minimum element, it will be less than 0. So it will be x minus some integer y. So it will be less than x, right? It will be less than x. So we will encode like this, and we will check when we pop. How do we understand that that was the value, that is the current minimum element that we are popping? We will just check if if the current value that we are popping x is less than the current minimum element. This cannot happen, right? Minimum element definitely means the current minimum element that we have till now. Now if x is less than minimum element, that means either we have calculated the minimum element wrongly, because minimum element should have been x, or it is because of the fact that we are storing a value less than x into the stack when we are inserting x, and x is the minimum element, right? So we can use this condition x less than minimum element to get the original, to understand that this is the value that is the minimum element is on the top of the stack. To understand this better, let's actually try this out with an example. So let's say we have 2 3 2 3, let's say 1 2 3 1, yes, 2 3 1. So initially minimum element is 2, right? So as the stack is empty, we will push 2 into the stack. As the stack is empty, we will push 2 into the stack, and we will mark minimum element equals to 2, right? Will not do anything. So one second, mark the minimum element should be cleared initially, right? Do we have a minimum? Have that I think it is cleared, the constructor, but yeah. So we have minimum element, we'll use the same thing, right? So it will be 2, current minimum element would be 0. So what we'll do is, we'll store x equals to what? We'll store 2 into x minus minimum element, that is 0. That is 2 into 2, that is 4. It will store 4. um Not exactly. So minimum element cannot be this. So for the first element, we'll just store 2 into the stack, right? And we will have minimum element equals to 2. For the first element, it actually doesn't matter, right? When we are removing. Next, when we are storing 3, 3 is less than minimum element, no, so we'll directly push 3 into the stack. Now for 1 it is important. For 1, when we are storing 1 into the stack, we have to somehow encode the information of 2, right? Because 2 will be lost after this. So what we do is we change x equals to 1 right now. So we change x equals to 2 into x minus minimum element. So that is 2 into 1 minus minimum element is 2 right now, that is 0. We stored 0 into the stack and we update minimum element to 1. Now when we pop from the stack, we see 0. 0 is less than 1, right? 0 is less than 1, which makes sense because we are storing a lesser value. So 0 is less than 1, so we know that this is the current minimum element that we have considered, right? This is the current minimum element that we have considered. So we will try to regain the original value of the minimum element that is already there in 1, right? We'll try to regain the previous minimum element. That will be what? 2 into minimum element 1 minus x, that is 0. So that is 2. The previous minimum element will be 2. So we will replace this minimum element to the previous minimum element and we'll remove this from the stack. Now we have 3. 3 is not less than the minimum element, so we'll remove this from the stack. For 2, 2 is equals to the minimum element, so we can remove, we'll definitely remove this, but we can not choose not to update the minimum element because it is the empty stack. So anyways, like we'll return for empty stack, we'll just return 0, right? So that's there. Anyways, that's the logic for this. Let's take a better example, right? Let's take a better example to understand this better, what we are doing. Let's take an example like 3, 2, 4, 1. Or let's just remove 4, 3 to 1. Because that is only important. So 3 to 1. First of all, minimum 3 is inserted and minimum element is 3. Then we have x equals to 2 coming in, right? So 2 is less than 3. So we have to somehow have this information of 3. What do we store in the array? We change x equals to, sorry, in the stack, x equals to what? We choose 2 into 2 minus 3. 2 into x minus 2 into x minus min element. That is 2 into 2 minus 3, that is 4 minus 3, that is 1. We store 1 into the stack and we replace this minimum element to 2. Next we have 1 coming in. So x equals to 1 now. And it is less than minimum element. So what do we store? 2 into 1 minus 2 into x minus minimum element 2, that is 0. So we store 0 into the stack and we replace this to 1. Okay, now let's say we are popping from the stack. We are popping from the stack, right? So what do? We see that the current element on the top of the stack is less than the minimum element. That means what? It means that minimum element is 1, this is 0. That means the current element is the minimum element, but this is encoded version. This contains the information of previous minimum element as well. So how do we get that? What was the formula that we had used that time? 2 into x minus minimum element. Let's call it minimum element dash, the previous minimum element, right? That is what we used. If we do right now, and current minimum element is equals to x, right? So if we do 2 into x, that is current minimum element, minus the top value, that is 2 into x minus minimum element dash. X is the current minimum element, right? So what do we get? We get minimum element dash, right? Minimum element dash, which is the previous minimum element. So we will get the previous minimum element. How do we get that? We'll do 2 into current minimum element, that is 1, minus the top of the stack, that is 0. So that is 2 into 1 minus 0, that is 2. So this is removed from the top of the stack and minimum element is made 2, right? Which is indeed true. Currently the minimum element is indeed 2. After that we have 1. 1 is less than 2, right? So we know that this is encoded again. So how do we get the minimum element out? Before this minimum element was, how do we get that out? Again, 2 into minimum element 2 minus the top of the stack, that is 1. So 4 minus 1, 3. So 3 is indeed the minimum element before this. 3 was the minimum element before 2. So we get that out. So we change the minimum element to 3 now. And we pop this from the stack. So like this, we continue, right? Like this, we'll continue. So this is the logic and it has order of 1 space complexity. So let's write the code for this. get minimum, it should just first of all we'll have a condition. If s dot size is equals to 0, it should return -1. Otherwise it should just return minimum element, right? For pop, what should we do? For pop, we'll write the pop later. First push, right? So if s dot size equals to 0, this is the first element we are pushing. So min element equals to x and s dot push x. Else if x is greater than minimum element, then we do nothing but just push it into the stack, s dot push. Else if it is less than minimum element, then what we'll do, we will update, right? So int card minimum, card element is equals to x. X is updated to what? 2 into x minus the current minimum element. We are encoding this like this. And s dot push x and minimum element equals to current element, right? So that is push. Now we'll come to pop. Pop is if s dot size equals to 0, will return -1. Int x equals to s dot top. Now if x is greater than equal to what? X is greater than equal to minimum element, just return x, right? Else what we'll do, we'll take the top element. So card element is mean element. We'll update the mean element. Mean element will be what? Mean element will be 2 into, we'll get back the previous minimum like this, 2 into mean element minus x dot top, sorry, x dot top, x minus x, and also h dot top, and let's do h dot pop here only, h dot pop. Mean element equals to 2 mean element minus x, and we will return current, right? We'll return current. So mean element, we have reset the mean element and we have returned current. So that should be the logic. Let's try to run this. Anyone has any doubts with this? Anyone has any doubts? So this is working fine. Let's try to submit. Okay, so it's done. Anyone has any doubts with this? Uh, Anyone has any doubts with this? Let me know if you have any doubts with the logic. It's a bit tricky. Like whenever you have a question, when you have to do in order of one space complexity, right? So in those cases, and you see that you generally need a space, some space to do that. Most in some cases you can go for like two-pointer approach, or you will find some way. But generally, in some cases you have to find a way to encode the previous data, right, or encode some data. So that should be a general thing that you should keep in mind, that uh, there can be cases where you have to encode the data, right? So that's about this question. I believe that you enjoyed the question. So let's quickly discuss about your homework. So the first thing is pretty simple. The two questions are pretty simple. stack using two queues. So you have to implement a stack using two queues, q1 and q2. Queue has a LIFO behavior and stack has a sorry uh, stack has the LIFO behavior and queue has a FIFO behavior. Yeah, queue has a FIFO behavior. So you have to implement a stack using two queues. Similarly, you have to implement a queue using two stacks. These are the two problems. The third is next greater element. Now, this is basically for every element of the array, you have to find what is the nearest element on the right hand side that is greater than the current element, right? So you have to find the index for all such elements. Now, variant for this will be next lesser element, previous greater element, previous lesser element. So try to extend your solution to handle those things as well. And I already have created a video in this channel for this problem, next data element and its variations. So if you want to take some help, you can definitely look into that. Is the 2x is the only logic or some other also work? You can, there can be multiple ways, right? You can find multiple ways to encode. Like you can do something like, let's say you know the number of values in the stack is within 100, so you can do 100 into 100 plus 1 into minimum element plus x, something like that, and you can encode in that way as well. So in that case, you can divide by 101 and get the minimum element, or you can take the modulo 101 and get the actual value. So that is also one way. There are multiple, like you can find multiple ways of encoding. This is one of the ways. Okay, all right. I believe if you don't have any other doubts, we can end the class here. Make sure to complete the homework, right? And like solve this problem definitely, because this problem is definitely very, very important from interview point of view. And so are the other two problems as well. So make sure to solve them as well.